大了，我不该废话。Okay, let's start.
All right, hello everyone. Here's our computer vision final project presentation. And our title is Integrating DLE for Enhanced Text-to-Image Synthesis in Galib Framework.
Here is the overview and motivation of our project. Our problem focuses on the recent popular Galip framework, which leveraged Clip M to generate the realistic and high-resolution images. Although the current Galip has been proven more effective among the recent popular GNs, it still encountered limitations regarding the image quality and relevance. Our goal is to enhance the Galip framework's capability for text-to-images synthesis by integrating the dialects with. Here you can see the original Gallic framework. And here is our model. We just integrate both the clipper-VIT and VAE of dialect to make a combined generator. Here's our torch detail. And first we do some model modification. And during the forward passing, after mapping the noise and conditional inputs, the generated features will pass through the VAE and we calculate the loss according to the VAE. Also, we involved both the encoding and decoding to ensure that the features moved through the mapping were further refined by the VAE structure. Also, the reconstruction loss and the KL divergence calculated by the VAE were combined with the existing GN loss to better guide the generator team in producing realistic images. Here is the loss function we compute for the whole generator model.
For the dataset, we are using the COCO dataset as a dataset for testing and training. And in this dataset, it comprises about 330,000 images. But due to the limitation of the computing unit, so we use the randomly choose 1% of the original COCO dataset and 10% of the original COCO dataset for our testing and training dataset. And for our experiment setup, first of all, we propose our data just like I said before. We randomly choose 1% of the original COCO dataset and 10% of the original COCO dataset. And also we set our hyperparameters for the discriminator and generator and also the add and optimizer. We also adjust our learning rate to get the better performance. And for the evaluation, we use the FID to check the performance of our module. And here's a table about our experiment results. And since we are comparing the original Galip and the Galip with the discrete VAE, we can find like although with a larger dataset, the Galip plus discrete VAE has a better performance than the Galip plus discrete VAE with the smaller dataset. But overall of our module is still worse than the original Galip. And here's our discussion. And since from the result from our experiment, we found like the integrating discrete VAE doesn't improve the performance of the original Galip. We found there might be several reasons. The first of all is a mismatch of the architecture. Since the DLE and the Galip are designed for different purpose, so the architecture difference in between these two modules may cause the worst performance. And also the limited data set is also might cause this problem since like the original Galip module are trained by the full COCO dataset, but we only train with 10% of the original COCO dataset. And also the hyperparameter tuning might also be a problem since like we didn't find research about integrating VAE to the Gallup, so we can't find a reference for the hyperparameter. So we tried it by ourselves, but so it might not be the best option of our hyperparameter choosing. And for the future improvement, first of all, we need to redesign the architecture to better integrate the discrete VAE with the Gallup framework. And second, we need to conduct a through hyperparameter search. The third, we need to find a more powerful computing unit to train on the full COCO dataset. For example, like in the original paper, they use the RTX 3090 to train the dataset. And last, we can just try different VAE module. For example, we can use VQGAN to integrate in the Gallup to see the performance. Here's
Here's
our
the reference
reference.
page.
Thank you.
Okay, and thank you for everyone.